There we go. There we go. Okay. Can everyone hear me?
Yep.
Yeah.
Cool. Right. So I'm just going to do a quick lightning talk on observability and computer vision pipelines and a project I plan on starting some point soon once other things calm down a bit and I get a bit more of my free time back. To introduce myself briefly, I'm Daniel McKenna. I also go by XD009642 online, so you might have seen me around before. I work on the code coverage tool, Cargo Tarpaulin, and I started ND Array Vision, that's been a bit inactive recently, but it's part of the Rust CV organization, and more work should be done on that in the future at some point. So what do we want to solve with observability? So computer vision pipelines, they're hard to debug. There may be a loss of stages, a loss of transformations on an image, blurs, feature extractions, say various detectors, etc. And it can make things potentially hard to debug, especially when so many algorithms tend to rely on heuristics. For example, I was looking at HOG, histogram of oriented gradients, and all of the implementations around OpenCV, PIL, ImageProc, dlib, they basically all return different things. And if you look at HOG, that's kind of how it, because of how it works. Often people will apply some sort of blur, a Gaussian blur, or say a mean filter, which they might not expose the hyperparameters of. They do a line detection like Sobel, but some might do something else, but most have tended to fall on Sobel. And then they do gradient binning and generate the histograms, but they might do the orientation gradients over 180 degrees, over full 360 degrees. So there's a lot of areas where things can change. And also OpenCV, when I tried it out, the default settings actually did multi-scale detections. So I think it actually created image pyramids and sort of did a standard HOG on each of them and concatenated all the gradients. So OpenCV's descriptor vector was tons bigger than all the other libraries I tried out. But then there's also potential other heuristics that people might have added in based on testing in their applications. And when you're trying to recreate a paper or someone else's results and you're relying on an implementation of a standard algorithm or standard algorithm, you may want to try and figure out where things have gone different between your implementation and their implementation. And as pipelines become more layered, you might want to be able to see what's happening at different points and to try and understand exactly how you're getting from A to B. And this can be useful for understanding the effects of your pipeline on your data or debugging issues. So what do people do now? Well, when I work on computer vision stuff in OpenCV, I've in the past used a visual debugger like ImageWatch, and I've built OpenCV with debug symbols so I can step breakpoints into algorithms and look at images like this when I've been trying to figure it out. Or if the code is stuff I've purely implemented myself, a lot of people will just add some lines which they later remove just to save images, and they'll expect the images using their operating system, which involves rebuilding your code, generating all these images, keeping them organized, and it can be a bit of a pain. But obviously we can do things better because we're engineers, and this is 2021. Come on. So what do we want to do? Well, instead of having to like rebuild code in debug mode or modify it to add things in, if we could just write code which can emit images to some sort of data sync that takes them in, and something which we can disable and have it 0 or near 0 cost. So we don't actually have to remove it from our production code if we don't want to. There's always gains to removing extra code from production, but if it can be as low cost as possible, it's potentially something we could keep in production and use for debugging. We have to collect and store these events. The file system may not always be available. It may have limited room. There may want to be source of sampling, ability to search for things, and other finer filtering, especially if you're running something like I do at my own work, where we have computer vision services in the cloud. You may get thousands of requests. So if you're going to keep this in production and enable this at certain points of certain requests, you need to source out some form of actually collecting and storing things, which is flexible and suitable for both local dev and production environments. And you want to be able to look at images, because that's all we're really here for, isn't it? Just looking at images. But as well as looking at images or inspecting matrices and their values, you might want things like color histograms, statistical analysis, various things which currently I usually just open up GIMP or write something with Python and Matplotlib and just do something a bit bespoke and hacky for each thing. If we're visually inspecting, we possibly also want to be able to compare and contrast inputs, see where something succeeds on one image and fails on another, what the difference is, or how changes in hyperparameters change our output. So my idea for solving this takes a lot of inspiration from existing tools and prior art. So from the Rust side, tracing. So I don't know how many people are familiar with tracing. Hopefully you all are. It's brilliant. It provides scoped, contextual, structured diagnostic instrumentation. So what this essentially means is that you can emit things like log events, and you can have span information and the context in which the log event happened. So for a computer vision pipeline, that context could be in our hog descriptor mentioned before. When we call the blur, the fact that it's called from hog and what's going in and what's coming out essentially act as the context. And then if we look at the context of the actual hog descriptor, all the stages it's taking and how it's changing things, that's all contextual information which can be a longer timeline. And with tracing, you have a subscriber or layer which collects tracing data and emits it. If it's disabled, it actually caches that it's disabled, so you only really hit the cost first time, and then it's just a simple branch comparison, which a CPU branch predictor will pretty much amortize and make 0 cost. You can always disable it completely at compile time if you so wanted. And for the next version of tracing, they're planning on integrating valuable, which is kind of like CERD. So anything which implements serialize or deserialize on CERD, you will be compatible with valuable. Because right now tracing can only send string, float, or integer data. It can't send arbitrary data. But this will mean that in our contextual event data, we can emit our images as events. And then we can have a subscriber which actually realizes their images and forwards them onto our system, which emits to our collector, which stores the images. And we can look at something which has been done with tracing, Tokyo Console, which is basically HTOP for asynchronous applications. So you can see everything that's been spawned. You can see the total time an async task has existed, how much time it's spent busy, how much time it's spent idle, number of polls, and you can get things like performance information like timing histograms. So we'd be creating something similar, but it'll be emitting images and not on a terminal UI because of the image part of it, but it can show similar statistics potentially. Ooh, skipped a bit ahead. So then for collecting and displaying, I've sort of seen OpenTelemetry work really well in production, especially going between different microservices, because it can keep the context of what service is calling what. And if you're working on something a bit more microservicey with computer images, you can see how your images are moving from service to service and how they're changing it. And also, you can use OpenTelemetry with tracing. There is a subscriber for it. But what happens is the application has a client which sends our trace data to a collector which stores them. And then we have a web UI which can query spans, display this essential timeline with what's being spawned where, all the hierarchical information of the pipeline. And it can work like this and sort of show associated data as well. If you drop something out, you can see a ton of fields and extra data values, as well as getting timing information. And then Image Watcher Bonsai. So Bonsai is like a visual programming thing that lets you inspect images in a pipeline. I haven't used it personally. I know Andrew's used it because he actually mentioned it to me, so I heard about it. But yeah, you can inspect these things to do the images from what I gather, and you can do a sort of more visual programming style and modify things. And we have Image Watch, which I've used. So then bringing all this together, I'm thinking of a system based on tracing, which collects the image data, emits it to some subscriber, which moves it to some standardized format for that, emits it to a server, which stores the images and any information we want. And then we can bring in a GUI application and we can query it and we can look at how the pipeline all works. And all of this will be completely disableable. And then we're looking at, like, when it's turned off, things in the order of like single nanoseconds just for disabled spans. But when it's on, getting rich, semantic, hierarchical data and being able to look at images and inspect everything at quite a deep layer level, and including things that are happening in libraries without having to recompile the library or reconfigure it between your development builds and production, which will hopefully keep the development workflow being a lot snappier, a lot more fluid, and make the sorts of hard bits of computer vision developments a lot easier. And that is me done for this lightning talk.